That's statistics for you, right? People get scared for really no reason. You're more likely to die on your way to a COVID vaccine than you are from something like that. So anyways, yeah, I've been feeling a little off. That's the problem when you get a vaccine, right? Your body it kind of makes you sick for a little bit because your body's getting used to it. Anyways, that's not very interesting. What you guys probably do want to talk about is um, the last type of problem, Chapter 11 problems. That I posted a video there on Monday that will allow you to hopefully solve most of those problems. And today I'll just go over a couple more types of them. This is a good example they have in here actually when they look at fraudulent data. If you go back to chapter 1 and we talk about self-reported data, one of the problems with, or one of the obvious things with self-reported data is that because people don't know, like let's say their actual weight, right? The background here is a random sample of 100 Californians is obtained, and the last digit is summarized here. So if you actually measure somebody's weight, like on a scale, like in the doctor, there's no reason that you're going to have any more zeros, 1, 2, 3, 4, 5s, or 9s in that number, right? If let's say you ask somebody how much they weigh, they might say, well, I weigh 160, right? But you might, if you actually got onto a scale, weigh 159 or 158 or 157 and so on and so forth. You're not any more likely to weigh 160 than 161. But if you ask somebody, they'll usually round to a 0 or a 5 because they just don't know. Right? A self-reported data set looks like this. Right? This is one way to scan whether or not you're getting fake data or actual real data. Would be you look at the last digit, and you would expect that the last digit would be uniformly distributed. And so they go through that problem there, and it's a nice little example. So you can go ahead and take a look at that. Now, obviously, the questions are going to be completely different because I posted this. But the idea is I just want you to see kind of maybe what kind of questions have been picked in the past. But, I don't necessarily want you to do these problems. I taught the course a little bit differently back then as well. But you can just kind of see the types of questions that are asked. And you can go through this. I'm not going to give you the solutions to this because you're just going to, I don't really even want you doing this. I just want you seeing what kind of format it comes in. You're much better off doing the problems that we've been working on this semester and reviewing what we've done in class. But yeah, you can take a look at this. So your best bet is to kind of go through, well, the Pearson website, do those first. But after that, if you need some more practice, and you can go, I kind of organize this a little bit better. So these are just kind of actual miscellaneous. Here's some additional practice problems for all the chapters that we covered, basically chapter 4 all the way to chapter 11 here. And the good thing about this, for example, this document here, again, and like most of those ones that I posted on here, the answers are, again, this is not, I need to see a little bit more than this, obviously, but this is just kind of their condensed answers, right? So an auto manufacturer has found that 57% of his passengers are people who currently drive the same make, okay? So you can actually, because they've already created a table, that's kind of nice. You can actually just kind of write down values as we see them here. So whenever you get something like this, right, this is a probability of something occurring. And so you can just write that down, right? So the expected probability of an event of somebody that has their own car is 57%, own same. 32 are first time, so that would be here. And 11% currently own a different make of vehicle. So 11% here. So you can just kind of add to this table here. When they added hybrid vehicles, a random sample of 250, that's going to be important. So we have 250 people that were surveyed, and then this is what they actually got, right? They found that out of 250 people, 129 had the same, 70 out of 250 are first-time buyers, and then 51 out of 250, right? This is the kind of thing with all Chapter 11 problems. Do the observed sales agree with the expected or the previous, right? With the expected distribution. And so in order to figure that out, you need to figure out how many did we expect to sell, right? If nothing had changed, right? Again, that's kind of the null hypothesis here, right? The null hypothesis is that nothing has changed. The expected distribution is good. In other words, probability of 1 is 0.57. Probability of car type number 2, 0.32. Right? The null hypothesis is always that, nothing changed. And then your alternative hypothesis is, oh, well, we introduced this new car, and so this new car is going to change the distribution. So it does not equal 0.57. Probability 2 does not equal 3.2. Probability of 3 does not equal. And if any one of these is true, then we can say that the hybrid vehicle has made a change, right? In other words, another way to state the alternative hypothesis, and kind of, again, we'll say this at the end, but a good way of saying it is the hybrid vehicle, right? The introduction of hybrid cars has changed the way people buy cars. Right? That's kind of this is how we're going to kind of prove it, is if any of these is not the same. And so what we'll do here is try and figure out a test score, right? Or test statistic, or you could do the critical score, but that's not as interesting right now. Let's do what is the expected and the observed distributions. Well, we know the observed, right? 129, 70, and 51, but what is the expected? Right, you always need to compare the observed frequency, and again, frequency is the key word here, with the expected frequency. So in this case, the observed is given, right? No problem. 129, 70, and 51. But the expected, we have to do a small little calculation. And again, I think I mentioned this yesterday, but that's kind of the complicated part with all of this stuff. How do I figure out what I should have sold? Well, if the probability was 57%, you'd have to times this by the sample size. The formula we would use in this case is the frequency of cars that you would expect would be your sample size times the probability or the share of the market that they're in. So there's a little bit of critical thinking there. Right? If 57% of the population normally buy the type, the same car that they had before, then you should have seen, right, whatever 250 times 0.51 is. And same thing over here. Sorry, 250. It's always 250 times whatever your, I don't know why I had 5.1. This should be 5.7. I spaced out, I guess. 0.57. This is 250 times the probability that somebody buys the second car. And this would be the expected number of cars. If 11% of the population buy a different car, then you should have seen this many. And again, Excel would be the best tool here to start crunching out these numbers. Right, so observed, expected, what should I have seen? I should have seen 250 times 0.57. And when you look at these numbers, right, the question is they are different, but are they significantly different, right? And the way you'd figure that out is, well, the first thing you can do is observed. Let's do the observed minus the expected, let's say. So all you gotta do here is go observed, figure out the difference between the two. And then you just keep building that formula. Right here you go O minus e to the power of 2. So you can just take this one here and square it. And then finally, the last step, O minus e squared divided by e. Right? The biggest difference was in the third category. So that makes sense that he's got the biggest test score. But again, you would sum this all up to get a total, and then that's your test score. So again, as you can see, kind of the hardest part is coming up with that. And each question is a little bit different. That's what makes this kind of a challenging part of the test. You have to really kind of think about how many would you have expected to sell, given some sort of distribution that we provide you with. So your chi-squared test score is 22 point something. Now we have to compare that, or just find, we could find a p-score. Let's do the p-value method, right? Because we know the alpha thing here is 1%. Right, we know that if alpha is 0.01, you could use a p-value, or you could use the table. I think I used the table last time, so let's do p-value. So how would I do a p-value here? Well, you could do right-tailed, and then you put in your alpha value, and then your degree of freedom. Chi-squared distribution returns the right-tailed probability. Yeah, and that's pretty much, that's what the p-value is. So my value is 22.61. My degrees of freedom is just 2 because I only have 3 categories. It's very small, so that's good. So, I mean, my value here, so the p-value was very small, 0.0001. Right, so again, the reason that's good is because if you were to make a little sketch here, right, this means that my chi-squared test score is definitely in the rejection zone. This would be the critical score. My value is like way the heck over here, right? Because this alpha is bigger than my p value here, right? So, you know, that's in the rejection zone. Okay. And then so essentially that tells us that the introduction of the cars has made a difference, right? There is enough evidence to claim that the distribution has changed, that car buying patterns have changed. Since the introduction of the hybrid. I was going to do the normal distribution one, but you can try it because the answers are right here. See, let me know if you get it. Right? I mean, it's not. I guess maybe I can just kind of give you a hint, but if you look at all of these types of problems with expected versus observed distributions, the challenge is figuring out the expected. Right? What is the expected frequency? You're trying to figure out what the null hypothesis is. Like every time, right? Isn't the null hypothesis the difficult part, right? What is the expected frequency? Well, that's the null hypothesis. Well, actually, the null hypothesis is always the kind of expected distribution, right? In this case, it would be normal. And how do you, well, so they're saying basically, we have 60 and under, right? It's already a little bit weird because the categories are not the same, right? This already gets me all pissed off, as you guys know. Under 60, and then you have all this. But the idea is that how would you figure, so this is what we observe, right? 30 students, fail, 30 students get a C, 140 get a B. And the question is that significantly different than if it was a normal distribution? Well, the way you would need to figure this out is what would you expect? Well, if the average is 75, right? And the standard deviation is 15, right? Kind of a classic distribution right there. How many people should get below 60? You can figure that out, right? You do that with a Z-score, right? If I want to know how many people are below 60, you use a Z-score. And you would say, I don't know, Z-score is 60 minus 75. 15. What's that, 1? I'm just going to do it like this for now. I don't think it'll make a difference. 60 minus 75 over 15, that's -1. And, right, again, you can either use your Z-score chart or Excel, right? Whatever you like doing the most. I would just alternate all the time if I was you. So 0.1587. I already have that one circled. 0.15. This is when you know you've done enough homework. When you've already got your Z-scores all picked out. Right? If your formula sheet looks like mine, I'm sure it's because you have an A+ in this course. Okay, -1.00. So 0.1587. So that means 0.1587 the population should get below 60. Right? The probability that a value is below 60, 0.1587. And then you would multiply this by the sample size to get your expected frequency. Right? If the probability of a normal distribution is 0.1587, and you would just do that for everything else, right? You would do that for all the other little sections of the pie. So 60 to 60, 60 to 60, then you go to 70, right? And so on and so forth. You figure out the probability or the area underneath these pieces of the pie, and then you multiply that by the sample size will give you the frequency. So the sample size here would be 60, 100, 300. And then you can figure out how many people are there, how many people you should see here, and then you do the same test that we did yesterday. So I'll let you have the fun of figuring that one out. But I kind of told you how to do it there. Let me try this second one here. So this one's a little bit more complicated because they're saying assuming a binomial. So what is this? It doesn't even give us any background, just a number of successes. This looks like a flipping the coin question, right? You flip a coin twice and you want to measure how many heads you have. So either you could have 0, 1, or 2 heads. And this is what we get. what should we have seen, right? So how many times did we flip this coin? Put this into a spreadsheet right here. So same kind of thing. So what I did observe was 41 zeros, 93 get ahead once, 66 times. I flipped the coin and I got 2 heads. I'm just trying to get some context because they don't really. What should I have gotten? Well, here we're going to have to use our binomial equation. So let's do that. So expected. So in this case here, I'm going to create an extra column because, well, how many total is this, I guess, right? Let me actually, I'm going to bring this to another sheet. I'm going to do a little bit more work on this one here just because there's an extra step. So let's call this the observed. Okay. Now this is going to be the outcome or the category, right? The outcome or category is either same thing in this case, 0, 1, or 2. Now how many times did I observe it? This many. Now that's cool, but what should I have seen? Well, what I should have seen is I would have expected a binomial distribution. Now, how many times, this would be 0. How many times should I see 0 if I flip it twice? And there's a 0.5 chance. Do I want cumulative? Doesn't matter. I'm just going to say 0. A quarter of the time. You could have figured that out a lot easier. I guess you don't really need to use binomial. You could just say, like, this should be 50-50 here, right? This here should be 50-50 if I just move this to a 1. Yeah. And I think this is going to be the same. A quarter of the time. Right? You could have figured this out easier than binomial. I guess they're just being kind of confusing, but this is what you should have gotten. In terms of, this is the probability though, right? So this is, again, where the extra step is. Because here they gave us the probability. In the first question, they said there's a 51% chance that a randomly selected person is from Washington. We had to figure that out. I had to figure out that there's a 25% chance you get 0, that there's a 50% chance that you get 1, and there's a 25% chance that you get 2. So that extra step here, because I need to do the expected frequency, because this is, again, this is a frequency here, right? So this is a common mistake that's done when you're solving these problems as well, is, they always give you the observed frequency. So you have to compare that to not the expected probability, but the expected frequency itself. So now here, I just have to take my sample size, which is this one, and then times it by the expected probability. So I should have seen 50 of these. And again, this is probably going to be 150. So there you go. And then now you do the same thing we just did before, right? You say, okay, now I need to know what is my observed minus my expected, and then so on. So again, the tricky part is just figuring out what should you have seen, and then once you do that, you just use your formula to do all this. Maybe I'll just show you quickly. So once you get your chi-squared value here, all right, so that's a pretty low chi-squared value, isn't it? But the thing here is we have a very small degree of freedom. So let's do the p-value method, just to switch things up. So once you have your chi-squared, your p-value, now then you put in your chi-squared value. And I only have 2 degrees of freedom because there's only 3 categories. So here I have a p-value of 0.026, which is greater than the alpha. right? So if you want to do all of this in Excel, that's cool. Just make sure that at some point you go back and you say, okay, what was my null hypothesis? Well, your null hypothesis is what is the expected distribution? It would be binomial. And your alternative hypothesis would be is not binomial. Yeah. You could make a little graph here. Whatever. Say something interesting. Once you start understanding the logic behind some of these processes, you'll find that it becomes more entertaining as well. So you have to wait a while.